So today, I'm going to talk about the flood frequency analysis and forecasting under non-stationary scenario. So here are a bunch of the questions in my first slides here. So particularly after 2013 flood, we have so many of the questions about the floods. So the first question, are the floods preventable? Answer is yes, of course no, because as a part of our nature, we cannot prevent the flood 100%. So then we will have another question, are the flood predictable? So in terms of the predicting the timing and also the magnitude of flood is not an easy task, just like the weather forecasting. Sometimes it's right, sometimes it's wrong. So then I think in the water resources management, one of the topics is the climate change impact on the water resources. So here, because we, in the city of the Calgary, we just had a flood in the 2005. So after 8 years later, so we got a flood in 2013 again, just 8 years difference, we got 2 floods event. So the people concerned if the climate change related to the recent flood event or not. So another question related to the climate change is that if the changing climate results in the extreme event getting more intense or frequent or not. So based on all the questions, so the last question, people want to know if there is anything we can do in order to reduce the flood damage. So in today's presentation, of course, I cannot answer all the questions listed on this slide here, but I would like to share with you about some of my data analysis results related to the flood. So here is my presentation outline today. So first, I would like to talk a little bit about the flood generation mechanism in the Bow River Watershed, and also talk a little bit about the potential climate change impact. And then I would like to demonstrate some of the limitation of the current flood frequency analysis approach, and then talk a little bit about the flood modeling and forecasting. So here, everybody know this map. So here is the Bow River Watershed. So in this study, I use the flow data from the Banff and Calgary and the Near Mouth. I also use the climatological data collected from the Banff and Calgary as well for this study. So first about the flood generation mechanism. So we know that floods in the Bow River Watershed can be caused because of the intensive rainfall, can be because of the snow melt, can be the combination of the snow melt and the rainfall, and can be the ice jam and others. For example, failure of the reservoir and the dam in the upstream of the Bow River. So here, because today I would like to focus on the peak flow. So in other words, that's an annual maximum daily flow. So here, because I use the flow data from the 3 gauge station on the Bow River from the Banff, Calgary, and the Near Mouth. So the 3 bar graph here show the number of the peak flow we observed in each of the months for the 3 gauge stations. So if you look at the plot A, that's the result for Banff. So you can see for most of the year, we observe the peak flow in the June, and sometimes we observe the peak flow in May and July, and occasionally in the August. If you look at the second bar graph on the right-hand side here, that is the result from Calgary. So same to the Banff. So we most likely, most of the year, we observe the peak flow in the June, and sometimes we observe the peak flow in the May, July, and occasionally in August and September. If you look at the bottom, the bar graph here, so you can see at the Near Mouth, the peak flow, we observe the peak flow in the June as well, sometime in May and July, and occasionally in the April and August and September. So from this graph, so we can see that for the Bow River and the peak flow, so there, even though there's so many of the reasons can cause the flood in the Bow River, I think from this result we can see that among these causes of the flood, the combination of the rain and the snowfall is dominant in the Bow River watershed. So then I also look at some of the relationship between the peak flow and the climatological variables. So as shown here, these 4 plots shows that the relationship between the peak flow and the rainfall amount at the Banff. So you can see the 4 plots shows the relationship with the annual peak flow with the rainfall amount, 1 day rainfall amount. So here, the 1 day rainfall amount is the daily rainfall amount we observed on the day when we had the peak flow. So the 2-day rainfall amount, that's the rainfall amount on the day we observed the peak flow, plus the rainfall amount the previous 1 day. So the 3-day and 4-day, that's the same, plus the previous 2 days rainfall amount. The 4 days rainfall, that's the rainfall amount on the day or we observe the peak, plus the 3 day ahead of the rainfall amount. So you can see from these 4 plots here, so you can see there is no clear or simple relationship between the peak flow and the daily and the multiple day rainfall amount at the Banff. So I did the same plot for the Calgary. So the same, from this graph, we still cannot see very strong relationship between the peak flow and the rainfall amount at the Calgary. However, if you compare these 4 plots here to previous slides, so you can see the dependency of the peak flow at the Calgary on the rainfall might be stronger than the dependence on the rainfall at the Banff. So that's the thing I can see from this analysis here. So then I look at the relationship between the snowfall and the annual peak flow. So here, I just simply use the total snowfall amount measured at the Banff and Calgary. I did not take the snow accumulation and the melting process into consideration. I just simply use the total amount of the snowfall to see if there is any potential relationship between the peak flow and the snowfall or not. So as shown here, we have the 2 plots. On the left-hand side, that is a result from the Banff. Right-hand side, that's result from Calgary. So you can see the difference between these 2 plots. So at the Banff, you can see certain of the relationship between the annual peak flow and the snowfall. So again here, the snowfall is calculated from the June of this year up to the previous July, so over a year. So you can see at the Banff, there's certain of the relationship between the peak flow and the snowfall. However, at the Calgary here, so we cannot see the same relationship at the Calgary. So based on this result, so we can see I got some of the conclusion. So in the Bow River Watershed, so we think that the rainfall combined with the snowfall dominate the high flow in the watershed. And then if we look at the headwater river ridge, for example, the Banff, the peak flow are likely closely related to the snowfall. So the snowfall maybe play a very important role. However, if you will look at the Calgary or further downstream of the Calgary, so the mechanism governing the peak flows might be very complicated compared at the Banff. So then the next is about the climate change impact. So of course, when we do the climate change impact study, so we usually use the trend analysis. That's a common tool used for the trend analysis. So in this study, I also use the non-parametric Mann-Kendall trend analysis to see if there is any potential climate change on the peak flow in the Bow River watershed or some of the change in the climatological variables in this watershed. So here, this graph shows the time series of the peak flow at the Banff in the blue, at the Calgary in red, and the Near Mouth in the black. So the dashed line here shows the trend. So you can see here, so we can see the very significant trend, the downward trend at the Banff and at the Calgary. However, we did not see the significant trend at the Near Mouth. So here, this is the time series of the peak flow again, but the data here, we look at the data from after 1970. So from here, we use the same Mann-Kendall trend analysis. But however, for this case, and we did not detect the significant trend at the Banff and the Calgary. And however, we observe the significant upward trend at the Near the Mouth. What does this mean? So that means if we look at the different time period, if we do the trend analysis, we may have the different result. So here is a trend analysis for the annual snowfall at the Banff. So if we look at all the data, so there is no significant trend. However, if you pay your attention on the data set after 1970, so you can see clear there is a downward trend. And before 1970, so you can see there is an upward trend. So here is the average air temperature at the Banff from the December to the March. So you can see very clear, so there is an upward trend. And the same thing we can see at the Calgary, there is an upward trend in terms of the average air temperature from the December to March. I also look at the average air temperature from April to May. So here is the time series for the average air temperature at the Banff. So even though we can see there is a slight upward trend here, but if you do the Mann-Kendall trend analysis, the upward trend is not significant. So I did the same for the Calgary. So you can see there is, even though we see some of the downward trend, but the trend is not significant as well. So I also look at the trend on the timing of the annual peak flow, because the timing of the peak flow can be very important indicator to show the potential climate change impact. So here the timing is a number of the days from the first day of the year up to the day when we observe the peak flow. So you can see there is a the downward trend here. So that means the timing of the peak flow becomes slightly earlier along with the time. However, when we use the Mann-Kendall trend analysis, the downward trend is not significant. So based on this preliminary analysis, so I got some of the conclusion for this part of the study. So it appears when we do some of the climate change impact study, so we look at the trend of some of the flow or some climatological variable. So the time series data always have some of the case there are the change point. So here we need to use some change point analysis to identify the change point. Why we need to do this? Because if you look at the before the change point and after change point, we may have the different result. So we need to include the change point analysis when we do the climate change impact study. So about the trend in the climatological variable, so we identify the significant increasing trend in the average air temperature at both of the Banff and Calgary, particularly during the December to the March. And the impact of the climate change might be highly complicated because we know so the rainfall, snowfall, air temperature, and other climatological variables have impact on the hydrological cycle in the watershed. So from this perspective, so we need to have the more comprehensive approach to assess the climate change impact in the Bow River watershed. So as a future work, the Dr. Katerina Valel, she was my PhD supervisor. She did climate change impact on the Able River. So I think we need to do the same study, climate change impact on the Bow River as well. So, of course, in order to evaluate the climate change impact in the watershed, we need more comprehensive approach to do the assessment. About the flood frequency analysis. So here for the Bow River, I use a 3-gauge station. So by playing with a different distribution, I found the GEV distribution is applicable for this analysis. So here I use a GEV distribution in this analysis. So you can see here this graph shows the result obtained from the Banff. Use all the available of the data at this station. So the red line shows the flood frequency curve generated based on the GEV distribution, assumption of the GEV distribution. And the blue dot, that is observations. So you can see, overall, we can see the GEV distribution fits the data reasonably. So let's look at some of the individual years. So the peak flow observed in the 2013 is the highest from the year of the 1909 to 2013 is the highest, which is followed by 1923, 1918, and 1974, and 1909. So here is a 2005. So if we look at the return period event of the return period year of the 2005 event at the Banff is around 1.5 years. So here is the result for the Calgary. So here, let's look at the individual years. So again, the peak flow we observed in the 2013 is the highest from the 1911 up to 2013, which is followed by 1932 and 1929, 1915, and 1916. So here is a 2005. So you can see the return period for the 2005 is around 15 years. However, if you pay your attention on the tail of the flood frequency curve, so you can see the GEV distribution didn't do good job here in this area. So because we see some of the difference between the observation and the red line here. So here is the result from at the station of the near the mouth. So if we look at the individual years, so we can see that the peak flow observed in the 2013 is the highest. But at this gauge station, we only have approximately 50 years of data from 1965 to 2013. And the 2013 years is followed by the 2005, and followed by 1995, 1967, and 2011. So here, I know there's a couple of the presentations this morning talk about the flood frequency analysis, and some of the presentation from yesterday talk about flood frequency analysis as well. But today, I would like to show some of the limitation of the current flood frequencies approach through some of the practice. So here is one of my practice. So here, I use the data from the Calgary. So I divide the data into the different time period. So then I did the flood frequency for each of the time period. So here you can see in the graph, we have the 4 different colors. So that's corresponding to 4 different time period. So the black is from the 1913 to 1952, and the red is from 1933 to 1972. And the green is from the 1953 to 1992, and the blue is from 1973 to 2013. So you can see the difference between the different color, right? So what does this mean? This means when we use a different data set, we might get the different result. For example, you want to know the magnitude of the 100 years return period event at the Calgary. If you use the blue line and the black line, so the magnitude is about 1,300 cubic meter per second. However, if you use the red line and the green line, so you can see the magnitude is around 600 or slightly below the 600 cubic meter per second. So you can see the big difference between the results. Another practice I did here, I use the Calgary data again. So here I use the data after the 1964. So what I have done here, so I use the blue line. You can see the different 2 color, blue and red. So the blue line, that's a result obtained in the flood frequency analysis when we use the data from 1964 up to 2013. So that means I include the data point from the 2013. The red line, I use the data from 1964 to 2012 without the data point from the 2013. I use the GEV distribution here. So you can see just one data point difference in the 2 data set. So you can see how big a difference here. So if you look at the numbers, I apologize, I did not use a good color for the table. So if you look at the numbers here, if you look at the 50 years of return period event, so if you look at the ratios column here, so the ratios of the 2 results from the blue line and the red line will be 1.53. So if you look at 500 years return period event, so you can see the ratios between these two results is 2.49. So when you design something, use a flat frequency curve, which one you are going to use? So that means there is a big uncertainty in the flat frequency analysis. So the result I have for the flat frequency analysis study, so I think that the current flat frequency analysis is very sensitive to some of the unusual data points. For example, the peak flow in the 2013. And uncertainty can be very big. So in this case, so we cannot just simply use certain of the time period of data, do the flat frequency analysis, see, oh, the 100 years return period event is 1,000 cubic feet per second. So you can see if you use another data set, you maybe got totally different result. So here's as a future work. So here, because as shown in the graph before, so you can see in the tail region, so the GV distribution did not do the good work, right? So in this case, maybe we need to use the two distribution or combination of the two distribution to fit the observation. So I would like to see if it's possible to use the mixture model to fit observation to improve the flat frequency analysis. So another future work I would like to do, because for example, at the Banff, we see some of the relationship between the snowfall and the peak flow. So if it's possible to introduce the relationship into the flat frequency analysis in order to reduce uncertainty in the flat frequency analysis. About the flat modeling and forecasting, I'm sorry I do not have any of the results to share in today's presentation, but I would like to talk about some of my research direction in the future. So when we talk about the flat modeling, so we can see we can use the conceptual model, physical-based model, and the black box model. No matter which model you are going to use, so the model should have the capability to simulate the flood generated by the different mechanism. So here, because as shown in this study, we see some of the change in the climatological variables. So we expect some of the change in the hydrological cycle. So here, when we develop a model, because of the unstationary condition, we do need to recalibrate the model in certain of the time period. So about the flat forecasting, so if we do the short lead time flat forecasting, so of course we can use the time series analysis techniques and the black box model to do it. But however, from the flood management perspective, so we will see the short lead time forecasting is not enough. So we prefer to have have the medium range forecasting. For example, couple of the days ahead forecasting or a week forecasting. So to do this, I think there is one way we can try. So that's a combination of the flood modeling to the weather forecasting. So in this case, of course, we can use the physical-based model and the conceptual model and the black box model as well. However, here we use the weather forecasting as an input. So you can see the accuracy of the flood forecasting is heavily dependent on the accuracy of the weather forecasting. So that's a disadvantage of this type of the flood forecasting approach. So in terms of future work for my research, so I would like to see if there is an approach we can develop to improve the model calibration and verification for the Bow River. And because we suspect the change in the hydrological cycle, so I would like to see if there is an approach we can use to model the process based on the process states. For example, if we can use the Kalman field techniques for the flood modeling and forecasting for the Bow River watershed or not. And of course, we need more reliable short and long lead time forecasting for the flood forecasting as well. So I would like, at the end, I would like to use the 3 photos I found from the internet to end my presentation today. So I think everybody in this room have the same experience. So one day you bring your umbrella, but at the end of the day, it turns out you didn't use it. So another day you bring your umbrella with you, and because we got really heavy rain event, your umbrella could not protect you from the rain event. And most ideal situation, you had the right umbrella at the right time. So that's really ideal situation. Just like the weather forecasting, flood forecasting, in order to reach the ideal conditions, there is a long way to go.